Since time immemorial, the human desire to communicate privately has driven the development of secret codes and ciphers. Ancient civilizations, from the Romans to the Egyptians, recognized the importance of protecting sensitive information, particularly in matters of war and diplomacy. Classical symmetric encryption, also known as secret key encryption, relies on a single shared key for both encryption and decryption. Imagine a locked box shared between two individuals, each possessing a copy of the key. From simple substitution ciphers to intricate mechanical marvels, these early encryption methods played a crucial role in shaping the course of history. The Caesar cipher, a shining example of simplicity in the world of encryption, exemplifies the earliest attempts at secure communication. Its underlying mechanism involves shifting each letter of the plaintext message a fixed number of positions down the alphabet. For instance, using a key of 3, A becomes D, B becomes E, and so on, wrapping around the alphabet for letters near the end. Imagine a Roman general sending a message to his troops: "Attack at dawn." Using a Caesar cipher with a key of 3, the message transforms into DDUWDFNDWGDZQ. While seemingly secure to the untrained eye, the Caesar cipher's weakness lies in its limited key space, the number of possible keys. A brute force attack, where an attacker tries every possible key, quickly reveals the plaintext message. Despite its vulnerabilities, the Caesar cipher's significance lies in its historical context. As cryptanalysts unraveled the simplicity of the Caesar cipher, the need for more robust encryption methods became increasingly apparent. Enter the Vigenère cipher, a polyalphabetic substitution cipher that emerged in the 16th century, offering a significant leap forward in cryptographic security. Unlike the Caesar cipher's fixed shift, the Vigenère cipher employs a keyword to introduce multiple layers of substitution, making it significantly more challenging to break. Imagine a grid, known as the Vigenère square, consisting of 26 alphabets, each shifted one position to the left relative to the one above it. To encrypt a message, a keyword is repeated beneath the plaintext. Each letter of the keyword then dictates which row of the Vigenère square to use for encryption. This polyalphabetic substitution, using a different alphabet for each letter based on the keyword, makes the Vigenère cipher more resistant to frequency analysis. While the Vigenère cipher remained unbroken for centuries, its eventual downfall came with the development of more advanced cryptanalytic techniques. Despite its eventual vulnerability, the Vigenère cipher marked a significant advancement in cryptographic thought. The Enigma machine, a marvel of 20th century engineering, stands as a testament to the intricate dance between encryption and cryptanalysis. Developed in the early 1920s, this electromechanical device, resembling a typewriter, enabled the encryption of messages through a complex series of substitutions and permutations. At the heart of the Enigma machine lay a series of rotating rotors, each wired to connect letters in a different order. As a letter was typed, an electrical current flowed through the rotors, resulting in a ciphertext letter illuminated on a lamp board. The rotors would then turn, changing the encryption pathway for the next letter. The German military, recognizing the Enigma machine's potential, adopted it for secure communication during World War II. The ability to decipher German military communications proved instrumental in the Allied victory, highlighting the crucial role of cryptanalysis in shaping the course of history. The history of classical ciphers is inextricably intertwined with the relentless pursuit of breaking them. As encryption methods evolved, so too did the art of cryptanalysis, the science of deciphering encrypted messages without knowledge of the key. Brute force, a straightforward yet computationally intensive approach, involves systematically trying every possible key until the correct one is found. While effective against ciphers with limited key spaces, such as the Caesar cipher, brute force attacks become increasingly impractical as the number of possible keys grows exponentially. Frequency analysis, a more elegant approach, exploits the statistical properties of language. Natural languages exhibit predictable patterns in letter frequencies. By analyzing the frequency distribution of ciphertext letters, cryptanalysts can deduce the encryption key and decipher the message. Known plaintext attacks, another powerful tool in the cryptanalyst's arsenal, leverage the knowledge of plaintext-ciphertext pairs to deduce the encryption key. Classical ciphers, particularly those with limited key spaces or predictable patterns, are particularly vulnerable to known plaintext attacks. Brute force, the most straightforward of cryptanalytic attacks, embodies the concept of relentless persistence. It involves systematically trying every possible key until the correct one unlocks the encrypted message. In the realm of cryptography, brute force attacks exploit the finite nature of key spaces. For a cipher with a small key space, such as the Caesar cipher with its 26 possible shifts, a brute force attack can be executed relatively quickly. However, as the key space expands, so too does the computational effort required. Modern encryption algorithms employ vast key spaces, often measured in bits. Despite its limitations against strong encryption, brute force remains a relevant threat, particularly against weak or poorly implemented cryptography. Language, the bedrock of human communication, possesses inherent patterns and regularities that extend beyond the meaning of words. These patterns, often subtle and subconscious, form the foundation of frequency analysis, a powerful cryptanalytic technique that exploits the statistical properties of language to break codes. At the heart of frequency analysis lies the observation that certain letters and letter combinations appear more frequently than others in natural language. In the English language, for instance, the letter E reigns supreme, appearing far more often than its counterparts. Classical ciphers, particularly monoalphabetic substitution ciphers like the Caesar cipher, preserve these underlying frequencies. By analyzing the frequency distribution of letters in the ciphertext, cryptanalysts can deduce the encryption key and unravel the message. While more complex ciphers, such as the Vigenère cipher, attempt to obscure these patterns through polyalphabetic substitution, frequency analysis can still be employed to identify repeating sequences and deduce key lengths. The success of frequency analysis highlights the importance of understanding and mitigating linguistic patterns in the design of secure encryption algorithms. In the high-stakes game of cryptography, knowledge is power, and even a sliver of revealed information can shatter the illusion of secrecy. Known plaintext attacks, a potent weapon in the cryptanalyst's arsenal, exploit the knowledge of plaintext ciphertext pairs to unravel the encryption key and compromise the entire message. The premise of a known plaintext attack hinges on the attacker possessing both the ciphertext and a corresponding portion of the plaintext. This knowledge can be obtained through various means, such as intercepting multiple messages encrypted with the same key, exploiting vulnerabilities in communication protocols, or even educated guesses based on contextual clues. Once a plaintext-ciphertext pair is obtained, the attacker can analyze the relationship between the two to deduce the encryption key or uncover patterns in the encryption process. Modern encryption algorithms, however, are designed to resist such attacks by employing complex mathematical operations and incorporating randomness into the encryption process. The vulnerabilities of classical ciphers, exposed by the relentless march of cryptanalysis, paved the way for a new era of secure communication modern encryption. Modern encryption algorithms, fueled by complex mathematical principles and computational power, provide a level of security unimaginable in the era of classical cryptography. At the heart of modern encryption lies the concept of computational security. Unlike classical ciphers, which relied on the secrecy of the algorithm itself, modern encryption algorithms are publicly known, their strength derived from the difficulty of solving complex mathematical problems. These problems, often rooted in number theory or abstract algebra, would take even the most powerful computers billions of years to solve, rendering brute force attacks practically infeasible. Modern encryption algorithms employ larger key sizes measured in bits to further enhance security. Furthermore, modern encryption incorporates randomness into the encryption process, ensuring that the same plaintext encrypted with the same key produces different ciphertext each time. The combination of complex mathematics, large key sizes, and randomness forms the bedrock of modern encryption, providing a robust defense against the evolving landscape of cyber threats. The journey through classical symmetric encryption techniques offers a captivating glimpse into the evolution of cryptographic thought. From the simplicity of the Caesar cipher to the intricate mechanisms of the Enigma machine, these early encryption methods played a crucial role in shaping the course of history. However, as cryptanalysis advanced, the inherent weaknesses of classical ciphers became increasingly apparent. The advent of modern encryption, fueled by complex mathematics, computational power, and a deep understanding of cryptanalysis, ushered in a new era of secure communication. Modern encryption algorithms, with their vast key spaces, probabilistic nature, and reliance on computational security, provide a robust defense against the evolving landscape of cyber threats. From simple shifts to complex algorithms, the quest for secure communication continues, driven by the relentless pursuit of outpacing those who seek to exploit our vulnerabilities.